Hello, everyone, and welcome back again. Now we are talking about the second part of statistics. As you know, this topic is associated with a previous video. So let's start. In the previous session, we were speaking about measures of central tendency. Now this goes hand in hand with that. The difference is that now, besides or like it has a different focus because instead of looking at a tendency from a general perspective or an average from a general perspective, now we're looking at average from a perspective of mathematics mixed with the statistics. That means a numerical perspective. So look, here we have the three measures of central tendency utilized commonly in statistics. Now, these are like widely known. So we will start. First, we have the median. It says it is the middle number of a set of numbers arranged in numerical order. So I want to clarify something. In this case, we are going to be getting the general perspective of the measures of central tendency when we have when we are not actually going to apply measures of central tendency to frequency distributions because it's a very specific process from statistics, and as you know, the idea here is to have the technical English terms, not precisely getting deep into the mathematical processes. That's not the focus here. The focus is to learn the technical English. That's why we are going to stick to the basic examples to get like the concept, terminology, and technical English of this topic, right? So it says it is the middle number of a set of numbers arranged in numerical order. So let's make an example. Let's go back to the notes, and as we have been doing previously, we are going to have this division that will tell us the limit of the previous session and the new one. So for example, let's suppose that we have some numbers, grades of an exam. I don't know, maybe 65, 81, 44, 55, 77, 70, and I don't know, maybe 70. Okay, so this is the median. And let us consider grades of an exam. So we have this. First of all, this is chaos because it's not ordered. We are going to order them, and the keyword here is sort. Now, sort is a way of ordering, but it's a specific way in which we are going to order something according to increasing numbers or decreasing numbers. Or if we are talking about alphabetical perspective, in alphabetical order from A to Z or from Z to A. It's not like a normal type of order. It's an order according to the criterion or the criteria of the alphabet or the Arab numbers. Again, from in increasing order or decreasing order. It's not this verb is special, right? It's specifically for this purpose. Okay, so we have let's order them. So the smallest one is 44. Then we have 55. Then we have 65. Then we have 70. Then we have 70. Then we have 77. And finally, we have 81. And there we go. Just checking. Yes. We have 1, 2, 3, 4, 5, 6, 7. So the number, we are going to use n to represent the number of values, right? I'm going to amplify a little bit here. So those are the parts, right? Let's go back to the presentation. So it says it's the middle number. For example, here, after ordering, we can identify that the middle number is 70, right? So we have already identified the median. The median equals 70, actually. So that would be the median. Remember the middle number after this numerical order. Now, there was a clarification. Let's go back to the presentation. It says, if the number of values in a set is even, then the median is the sum of the two middle values divided by 2. So there is an extra thing to consider. Let's go back. So first of all, let's try to remember even number. An even number is a whole number that is divisible by 2. There we go. Sorry, this number. Okay, a whole number that is divisible by 2 into 2 equal whole numbers. That is an even number. A whole number, or we can say also an integer that is divisible by 2 into 2 equal whole numbers. In other words, a whole number that has an exact division by 2, an exact half. That means we don't have decimal points or we don't have fractions. So for example, 10 divided by 2, the result is 5. 10 is even because 5 is an exact number, it has no decimals. And the other part would be an odd number. That would be exactly the same only the opposite, right? So we have an odd number, sorry, this is an integer that is not exactly divisible by 2, therefore not resulting into 2 equal whole numbers. In other words, an integer or whole number that when divided by 2 will not give us an exact number. That means it will not give us a number that has no decimals or fractions. It is going to give us a number with decimals or that can be represented by fractions. For example, 9. 9 divided by 2 is 4.5. It's not an exact number because it has decimals. So 9 is odd. In other words, even numbers ending in 0, 2, 4, 6, 8, odd numbers ending in 0, 1, 3, 5, 7, 9. Did I miss any? 0, 2, 4, 6, 8. There we go. I am going to add for you to know that we also have prime numbers. These are the ones whole numbers divisible only by themselves or 1. For example, 17. You can only divide 17 by 1 and it will give you 17, or 17 by 17 and it will give you 1. With any other division, you are never going to get a whole number. That's the situation. In this case, only with itself or with 1 will give you an exact number. That means a number without decimals. So keep that in mind. For example, 1, 3, 5, 7, 11, not 9, right? Because 9 can be divided by 3. 13, not 15, because 15 can be divided by 5 or by 3. 17, and so on. So let's go back. We have the median equals 70, but this is because this distribution has 1, 2, 3, 4, 5, 6, 7 numbers. It's an odd distribution. With an odd distribution, we just check the middle number and we have finished. How can we have identified the middle number? There are the same numbers at the left than at the right. We have 1, 2, 3 here, 1, 2, 3 here. So that's correct. Assuming a hypothetical situation, we can have here another number, and this would be an even distribution. Now we have 8. We have to take the two middle values and make a little operation of summing and divide it by 2. After summing and divided by 2, 70 plus 70 would be 140 divided by 2. This would be 70 exactly. In this case, coincidentally, the median would be the same even if we have an extra value here. But this is just hypothetical. Normally it changes, right? If you add another value, because the two numbers in the middle are not always going to be the same. So I'm going to raise to 84 because this was hypothetical. And let's continue. Let's go back to the presentation. Now we have the mode. This is actually a lot easier because you just have to look for the most frequent value in a set. Which one is repeated in the most of the cases? That's the answer. In this case, clearly the only one that is repeated is 70, so the mode is also 70. That's pretty easy, right? Let's go back. However, there is a clarification that says a set can have more than one mode. If it has two, it is said to be bimodal. So for example, if two numbers are exactly repeated in the same times, let's go back. For example, just imagine that another score was, instead of 55, was 65. This distribution would have two modes, 65 and 70, and it would be bimodal, right? Because they tied in the number of times they repeat. But that's not the case. Let's go back. So the final one, look, it says it is good, it is useful for the comparison of grades of a test, precisely as we did with the mode. Useful when the members of the set are very different, like in the grades of a test. Finally, you have the mean. The mean is the sum of all the values in a set divided by the number of values. Simple as that. The mean of a whole population is usually denoted by mu, this is a Greek letter, while the mean of a sample is usually denoted by an X bar. Let's go back. So let's look for this symbol. Remember, this is a sample because we don't have all the exams in the world, right? Just in this case, 7 exams. So it's just a sample. Imagine that the class is of 30 students. and we only have a portion. This is a sample. We will talk about this term later on. So let's look for the right symbol. So it says that it's the sum let's use this like that. The sum okay, something like that, right? This is the mean, the sum of all the values. This is xi to n divided by n. So the calculation would be, I'm going to copy this equation expression. Amplify a little bit more, and we have 45 plus 55 plus 65 plus 70 plus 70 plus 77 plus 81 divided by 7 equals so I'm just gonna make this calculation. We have 44 plus 55 plus 65 plus 70 plus 70 plus 77 plus 81. Sorry, there was a little mistake here. It's 44 plus 55 plus 65 plus 70 plus 70 plus 77 plus 81. This gives us 462 divided by 7. And we have that the value is actually equal to, I'm going to make the operation, exactly 66. Now, in this case, we have an exact value, right? This doesn't really happen always, but I mean an integer, right? It normally has decimal points, but that doesn't really matter. It's just a matter of chance. So there we go. This would be the mean, right? So we have the three values. I'm going to report them here. Just to have it all together. So those are the three measures of central tendency. Now, what reflections can we make? Look at this. Something interesting is that even though 66 is relatively close to 70, it's not precisely so close, right? It's not like 69 or 71 or 69 point something or 71 point something or 70 point something. This is indicating something, and I have to say, right? Let's finish this part. the mean of a whole population is usually denoted by mu, while the mean of a sample is usually denoted by x bar. Now, an interesting reflection is that since the mean is taking into consideration all the values, we could say that it's the measurement that is more reliable. Sometimes. Please, this is the reflection. The mean is not always the most reliable value. Why is this? Even though your argument is valid to say that since in the operation we are including all the values, this is not entirely something for sure to make it the most reliable. It really depends on the values. Imagine that, just imagine this, imagine that the day of the test someone was maybe very distracted, or someone didn't study something, or didn't study something at all. That means someone was lazy and didn't study anything. And let's suppose that this grade wasn't 44 and it was, I don't know, maybe 20, because this person was lazy and he or she answered only what he or she remembered. So a hypothetical situation here would give us here a 42. I'm not going to make all the operation, but if you substitute 44 with 20, I'm going to make the hypothetical second value. Look, this is a hypothetical second value. I don't like how it looks. Do it to everything. There we go. Now, I am not going to make that calculation on the screen, but you can do it in your calculator. You substitute the 44 and you utilize 20 instead of 44, right? If you do that, I'm going to make the calculation. 20 plus 55 plus 65. 20 plus 55 plus 65 plus 70 plus 70 plus 77 plus 81 equals 438 divided by 7. Look, the value goes down to 62.57. Now, this hypothetical value is actually lying, right? So this is false, right? Because the tendency is not that, right? Let's go back here with the original number. Look, the tendency is that people got actually nice grades. That means 55, maybe it's not the best one, but it's still almost 60, right? Here, you are saying that the tendency goes a little bit closer to 60, and if you see here, the tendency goes a little bit closer to 70, because 81 is so far away from 60, for example, but it's not so far away from 70. It's exactly in the middle of 81 is, 70 is in the middle of 81 and 60, almost, right? Almost there. So you would be lying if you say that the average or the overall score is 62. It sounds like a more difficult exam. It is implying that most of the grades were 60, right? And actually we have really good grades with this 270, this 77, and this 81. So the reflection is the mean is not always the most reliable value. It is the most reliable value as long as the values are not so separated one from the other. That means they are not so dispersed, right? If they are not so far away from one another, the mean is the best one. But if there is a strange value, like so low or so high, because it could be also 100 here, that value is going to somehow infect, this is obviously figuratively speaking, it's going to infect our mean. When we have a very strange or weird or unusual value, the most reliable value would be the median, okay? So the median is the most reliable when there is when there are like really strange extreme values, right? So big or so small. But if they're consistently separated, maybe not exactly right, but very close, all of them, we can say that the mean is the best one. So there we go. Let's continue. And we have the measures of variability. Now, we are going to learn this from a perspective of, because they're really important too. Look, the average score in a distribution is important in many research contexts. So too is another set of statistics that, this is the concept, set of statistics that quantify how variable or how dispersed the scores in a data set tend to be. This is the definition of measures of variability. How dispersed, how far away something is from the mean. Look, sometimes variability in scores is the central issue in a research question. Variability is a quantitative concept, so none of this applies to distributions of qualitative data. Now look, now we are not focused on the central tendency, but on the distances from the mean, from the center value. How dispersed the values are from the mean. That's the purpose. The first one is the range, is the difference between the largest and the difference between the largest and the smallest value of a set. Let's go back. In this case, the range would be 81 minus 44. That would give us 81 minus 44 would give us 37. Now, this number is not so useful because it depends on the extreme values. And as you know, the extreme values are so far away one from the other. But the idea is to use this. It is useful for making frequency distribution. Why? Because we use this number for an extra calculation when we make frequency distributions, okay? But we are not going to do that. Again, the focus here is to learn the English, not so much the numerical calculations. But that's the purpose of the range. Normally, it is not like a useful value by itself. It is used for something else, but not by itself. So there we go, we have the range. Let's continue. Look, it's not very useful because it depends on the extreme values, which may be distorted. Now, this is an interesting word. In this context, distort is something that twists or like affects a natural, normal, or original condition. That means it wouldn't give us a real picture of the situation. Here we are saying that the differences are 37 between or among the grades. That is not correct because some grades are really close to each other. So this is actually lying. So again, that is distortion, right? It causes a twisted and not adequate perception of the natural, normal, or original condition. That's like the definition of distortion. It gives us something that it's not precisely what is naturally happen, right? A version that is non-existing, right? Let's go back. Then we have the variance. The variance is a measure of how items are dispersed about the mean. Look, how items are dispersed. How items are dispersed about their mean. This is what I was telling you. Here we're actually interested in knowing the distances from the mean. That is our real interest here. The variance of a whole population is given by the equation sigma squared equals this value and the variance of a sample. So look, we are talking about two very important concepts, okay? Population and sample. I'm going to use a distinctive color for them because they are really important. Now, let's clarify these two concepts before we continue. So a population is the entire number of elements that are found in a particular group. This is like a very general definition. Why? Because there are also other definitions that are exclusively directed to inhabitants, right? For example, a definition for that is exclusive for human purposes, exclusive for human elements, is that a population is the whole number of people or inhabitants in a country or region. But this definition is it's very particular. We have to make it more general because in statistics we can quantify anything whatsoever. So I prefer to say that a population is the total number of elements that are found in a particular group, in the complete group, of course. So that's a more accurate definition. Then a sample, it's one portion or only one extraction or a small group that is taken from the complete group. In other words, a sample is part of the population, is within the population. So why are we separating these two terms? Because they are useful for future calculations. So we have here the variance for a whole population is given with this equation. This symbol is called sigma, and it's sigma squared, and we have this symbol is called mu, and the n is the number of elements in this case in a population, and the variance of a sample is calculated differently with an s and the mean, but the mean of a sample, right? So now let's check the definition of a standard deviation. Please, it's not desviation. The thing is that in Spanish we say desviación, but in English we don't pronounce and we don't write the S. It's deviation, okay? So the standard deviation, sigma or S for a sample, is the square root of the variance. I'm going to stop here and show you the symbols that are actually used. We are here on the notes. We are going to go to the next page, and we have this table. So for the mean of a population, remember, I clarified these words here. Parameter are the values that come from the population, and statistic are the values that come from the sample. This is a very important comparison in statistics. So for the mean, for the population, we use mu, and this is the symbol mu. And for the mean of the sample, we use x bar as we did before. And the standard deviation for the population, we use the symbol sigma. And for the sample, we use the symbol s. These are important symbols. Remember, standard deviation is going to be a reference of how dispersed the values are from the mean. This is going to tell you how far away data is from the mean, the same as here, right? Now, I want to show you, we were checking this, I want to show you a graph of how this is represented. So look at this graph. This is a bell, and we are going to assume that the distribution of our data is within or inside this bell. We are going to assume that This is the graph of the distribution of our data. Now you can check here. This is for a population, but it could be perfectly for a sample. So why? Because we have mu here, it could be x bar. So look, here we're going to check how the standard deviation works with our mean. As you can see, 68% of the data is within the first standard deviation, because remember that the variance is sigma squared. When you extract the square root, you're going to get two values, a positive like this one and a negative like this one. So you have your mean, you're going to sum the mean plus one standard deviation, and you're going to subtract the mean with one standard deviation. 68% is within. If you use 2, 95%, and most of the data is going to be within the 3 standard deviations. That is like the logic of the values in statistics. This is just an example, a general example, and that's why we are checking the dispersion. How far away the values are from the mean, right? This is the idea. So let's go back to the presentation. There we go. Sorry, the standard deviation is the square root of the variance. That's why we have two values, one at the right, one at the left. And we have the relative variability. The relative variability of a set is its standard deviation divided by its mean. The relative variability is useful for comparing several variances. Look, the standard deviation divided by its mean. That means that, remember, it is better if our standard deviation is as small as possible. Look, if it is as small as possible, we are going to get more concentrated data, right? If we have a big one, the data is going to be more dispersed, right? That's like the situation here. So the idea is to have the smallest standard deviation as possible to make that consistency of distance between or among the values. And that's like the ideal scenario. Obviously, in reality, this is not something that happens, right? So there we go. So this is basically all about measures of variability. And now I just want to finish with, remember that we were speaking about the range. Let's go back to the notes. Now, we said that the range is useful. We said that the range is useful for making frequency distributions. Now, I want to give you a little explanation of how this works, right? Because we only said that it was the difference between the highest and the lowest value. But let's check its utility. Now, first, let's consider this situation. Look, read here. Range is useful for making frequency distributions. Now, let's imagine this situation. People of most ages are sent, people of most ages are sent to a medical test in order to develop a vaccine. Why? Because remember that a vaccine for healing specific sickness, like attacking a virus or attacking a bacteria, something like that, has to be tested on people of all ages, right? Or at least almost of all ages. Now, we have this new N. It says that in this examination, there were 256 people. And we want to know, in this case, the distribution of the table. Now, look, for big distributions greater than 10 values, we have to use a frequency distribution. I am going to give you this example, like a very quick example, so that you see the utility of the range as a measure of variability. Now, let's suppose that they were 256 people of all ages, right? To develop this vaccine, and we have this important value. It says the oldest person is 91 years old and the youngest is 10 years old. Remember, the range is the difference between the highest value or the maximum value and the minimum value. The difference between the maximum and the minimum or highest and lowest. So we are going to calculate the range. It's simple, right? Just, again, range is the maximum number minus the minimum. So we have 91 minus 10 equals 100. And now we are going to learn a new concept in descriptive statistics, which is the number of classes. What is a class? We will talk about that in a little while, but for now, let's just learn the formula. This is the Sturgis formula. This is due to the last name of the person who developed the formula. The formula is K. K means the number of classes is 1 plus the logarithm on base 2 of n. And as you know, this can be expressed using a change of base according to math. So it can be K equals 1 plus logarithm of n. It's logarithm in base 10, right? But when it's base 10, we normally don't say 10. So it's logarithm of n over logarithm of 2. And we can also separate this using algebra, and we have like this. 1 plus 1 divided by logarithm of 2 times logarithm of n. This is a number, right? We are going to use 3 decimal points. And there we go. 1 plus 3.322 times the logarithm of n. What is n? The number of patients that were sent to develop this vaccine. In other words, we have that number here, right? 56 people. 256 people. So we place that 256 and we get that the number of classes is 9. Again, I'm going to clarify this number in a little while. Then the width of the classes. Here you can see the utility of the range, because to calculate this h is the width of classes, you have to divide range over the number of classes, r over k. In this case, the range was 81 and the number of classes was 9. So in this case, 81 over 9 is 9. Let's check this on the final distribution table. Here you can see the final product. So classes are the number of intervals that we are going to establish for big proportions. In this case, 9 classes, or in other words, 9 intervals. That is the number of classes. And the width of classes is the distance that you can get when you subtract the highest, the higher and the lower values of an interval. 19 minus 10 equals 9, right? And you have all the intervals and the frequency. If you make a sum or an addition of all these numbers, you're going to get 256. That means that here are the 256 people. The idea is that you can describe statistics in a better way using this distribution of data. Now you can say that, for example, the youngest people were the highest number, for example. You can say that the oldest people were the lowest number in this examination for the vaccine, right? So there we go. We have 9 classes, width of the class of 9, and we have these frequencies that in total will give us 256. But the idea was to emphasize the utility of the range as part of the width of classes in order to build this distribution table. So that's all for this second part of statistics, and we have talked about, in general, descriptive statistics. Thank you for watching and learning a little bit more.